In this video, we're going to get an introduction to the Rankine cycle. And so previously, I talked about the Carnot cycle, and I emphasized that the Carnot cycle is something that has not been actually applied or produced in the real world. Close batch process. Okay. And one of the main reasons for that is, it's hard to get a frictionless piston. It's also pretty hard to actually do an isothermal expansion. So no easy way to implement isothermal expansion. So there's many reasons for why the Carnot cycle has never been achieved in real life. And furthermore, when it comes to just engineering, processes to extract work from some sort of chemical, most engineers would prefer to work with an open, continuous system process. So most prefer to design open, or at least continuous processes. And the reason for that is just, practicality. It's just a bit easier to get higher efficiencies. Okay. All right. And so one example of a cycle that's a continuous process is the Rankine cycle. Okay, so this is something that has been applied in real life, and it's a common type of process that you'll see in power plants all across the world. Okay, and so the Rankine cycle, what it involves is 4 different unit operations. So it involves a boiler, involves a turbine, involves a condenser, and then at the end it's also going to involve a pump. Okay. All right, and so with the Rankine cycle, there's 4 different unit operations, and there's also going to be basically 4 different steps that are involved. Okay, and so in the Rankine cycle, what we're going to start with in this first stream is that we're going to be dealing with some sort of liquid that's at a high pressure. Okay. Right, and so in this first stream, it's a liquid. There's no vapor, or in other words, the quality of this liquid, it's going to be equal to 0. Okay. All right, and so this liquid's going to be at some temperature, some high pressure, and also we could talk about its entropy as well. Its specific entropy is going to be S1. Okay, and so this high pressure liquid, it's fed into a boiler, and in this boiler some heat is put into the process from a hot reservoir, QH, and this heat basically heats up the liquid and then causes it to evaporate, so that when it comes out of the boiler, it comes out as a high pressure vapor. Right, so it's completely a vapor, so its quality is 1. The temperature of stream 2 is going to be greater than the temperature of stream 1. The pressure is going to be the same. In the boiler, the fluid isn't pressurized or anything, so it comes out at that same pressure. But because it's now a vapor rather than a liquid, its specific entropy is going to be greater than the stream 1. Okay, and so the boiler basically just boils the liquid to create a vapor, And then this vapor is fed into a turbine where it's then depressurized to form a low pressure vapor. Okay? Where its temperature is less than the temperature of stream 2. Its pressure is lower, right? It's depressurized. But typically, when it passes through the turbine, it's done in such a way that it's adiabatic. So the entropy of stream 3, we're going to say it's going to be equal to the entropy of stream 2. Now, of course, when it's being depressurized in the turbine, the whole point of a turbine, it's supposed to extract work from a fluid. And so this turbine extracts work during the depressurization process. Okay. The other thing I want to point out here is this is a low pressure vapor, and potentially you could either still have some sort of superheated vapor, or you could even depressurize the vapor all the way down to its saturation conditions. And so the quality of this vapor, when you depressurize it, can be anywhere between 0 and 1. So what that means is you might actually have some liquid that comes out of the turbine as well. Okay. All right, in any case, this low pressure vapor is then fed into a condenser where it's further cooled. So heat is extracted from the vapor, QC. And this cooling then basically just turns that vapor completely into a liquid. Okay. So what we have is a low pressure liquid where this is done isothermally, so its temperature T4 is still equal to T3. Pressure is also the same. But the entropy, because it's undergoing a phase change, is going to be from a vapor to a liquid. Its entropy is going to be less than stream 3. And so, just to emphasize, this is completely a liquid now, so its quality is back down to 0. Okay? And then in the final step, this liquid, this low pressure liquid, is then fed into a pump, where this pump basically applies work onto the liquid to bring it back up to the high initial pressure. Okay? And so the temperature of stream 4, as the liquid goes through the pump, its temperature slightly increases. Its pressure definitely increases. That's the whole point of a pump. And then because it's being pressurized a little bit, the entropy of stream 1 is going to be a little bit less than the entropy of stream 4. Okay? All right, and so those are the basic steps of the Rankine cycle. We could also visualize these steps on a temperature entropy plot. So this is T, this is S. All right, and so if we start here with stream 1, basically in the boiler we add heat to heat up that liquid to its boiling point and then evaporate it. Right? And so this plateau that we see here, this is when when something starts boiling, it just stays at the boiling point temperature. So that's why that temperature plateaus. And then once all the liquid becomes vapor, it then starts increasing its temperature again. Okay? So this is the boiler step. Then in the turbine, the point of the turbine is it depressurizes that vapor and also decreases its temperature. But it's done in an adiabatic manner or an isentropic manner. So while the temperature drops, the entropy stays the same. Then that low pressure vapor goes through the condenser where it's just completely turned into a liquid. So because of that phase change, the entropy changes. But this is all done isothermally, so the temperature does not change. And then the pump, you know, pressurizes that liquid, so it slightly increases the uh, what's it called, the temperature of the liquid as well. And also, I realize here I wrote the sign backwards, right? And so the reason the entropy for S1 is greater than S4 is because of that slight temperature increase as well. Okay. In any case, this is how you could visualize the Rankine cycle on a temperature entropy plot. In terms of efficiency of the cycle, of the Rankine cycle, what we want to take is essentially the total work for the process. And so the work of the turbine, so which I call WS, it's going out of the system. And what we want to subtract off is the work of the pump. That'll give us the total work of the system. And then we want to compare that to the heat that we need to put into the system in order to boil that vapor. Okay. And so this is how you would calculate the efficiency of the Rankine cycle. And in general, this efficiency can either be equal to or slightly less than the Carnot efficiency, which once again was just 1 minus Tc over Th. All right, and so that depends on if your Rankine cycle is operating reversibly or if there's some irreversibilities that are affecting the process.